Thank you very much for inviting me here to speak at KAIST again. So the topic that I'll be talking about is actually related to the talk that I gave a year ago. It's basically the same project, and most of the a significant part of the talk will be the same as the one that I gave a year before. But since the last talk we did make some progress, so we will also talk about some new results in the sense that we can now strengthen our conclusion quite a bit. So firstly, the work is a collaboration with Harry Beck here and Farbot. So I will state the statement. The motivation for this project is that we want to generalize a classical theorem regarding Riemann surface. So there's this Kazhdan's theorem. There are many theorems named after Kazhdan. This is only one of those. So I think this is probably not the most famous Kazhdan's theorem. Yeah, it's interesting though. So we saw this theorem in the appendix of a paper by McMullen, and he claims that this is in Kazhdan's work. But we read the paper, and we wasn't able to see anywhere in the we wasn't able to see how to deduce from the results in that paper to this theorem. So I'm not entirely sure whether or not this is exactly the same as is of the same generality as the theorem proved by Kazhdan himself. So the theorem goes as follows. So S is a compact Riemann surface. We define the canonical metric this one is a Riemannian metric defined as the canonical metric of a vector. V is the supremum of all the omega. Omega is holomorphic one form on S. And then the norm equals 1. So here the norm of a holomorphic one form is just do conjugate and then multiply with the original form and do integration over the whole surface. So this one, the supremum of omega pairing with V. So we have a one form and have a vector, so we can do the pairing and take absolute value. So we can verify, it can easily be verified that in the case where S is a compact Riemann surface, this one is basically just the, so this one equals can be written as a sum of omega I squared. So where omega I are of a normal basis of the space of holomorphic one forms. In particular, this one actually defines a Riemannian metric. So the statement is that if we have a sequence of normal covers of S, S1, S2, S3, etc. The canonical metric on Si is the pullback of a metric Di on S, then the limit of Di exists and is proportional to the hyperbolic metric. In other words, it's a Riemannian metric of constant negative curvature. So this is the theorem attributed to Kazhdan. So the motivation is that we are trying to generalize this theorem. So the generalization that we managed to obtain is as follows.
Wait, you need an assumption on the cover.
What? Oh, I see. Yeah, I see. So in the classical theorem, there's another. Oh, yeah, because yeah. So it's easy to see that the hyperbolic metric is exactly the canonical metric for the unit disk. So we have, so here we want these coverings to be closer and closer to the unit disk. So we have the intersection of pi1 of Sn equals just the identity. In other words, these covers should approximate the normal cover. The universal cover. Okay, so this is the statement of other people's theorem. So what we have done is that we are able to generalize this theorem in several directions. So we have generalization. Firstly, if we remove the condition that the intersection of the pi1 of Sn equals the identity group, we still have convergence. But the limit will not be hyperbolic. So there's another earlier paper where we are able to generalize this statement to graphs. In other words, we can consider all the S to be graphs, and then the canonical metric can be defined using counting the number of supporting trees on the graph with some weighting. But that one is, I think that's the stuff that I talked about a year ago in also this seminar. But so now we will focus not on the graph case, but on the other case, which is the manifold case. So we have another possible generalization. S can be replaced by any compact Riemannian manifolds. In other words, a smooth manifold with a smooth Riemannian metric, and it has to be compact, obviously. Then we still have the convergence of the canonical metric. So here we can no longer define the canonical metric in the same way as before, because for Riemannian manifold, for example, for three-dimensional Riemannian manifold, we cannot have there isn't a complex structure, and for even-dimensional Riemannian manifold in general, it doesn't have complex structure either. So we have to have an alternative way of defining canonical metric, so that in the case when the manifold is a surface, it's the same as the previous definition.
And why DI must exist?
I see. So the fact that DI exists is because we are using normal coverings. So normal covering means that it's transitive, like the preimages can get sent to each other under the deck transformation, and deck transformation is isometry. And because in this definition, in the early Kazhdan case, the canonical metric is conformal invariant. So if it's isometry, then it's of course conformally invariant. Then of course the canonical metric will remain unchanged. But in the Riemannian manifold setting, we cannot really guarantee that it's still conformal invariant. Actually, I'm not sure whether or not it's conformal invariant. It's something that we can check, which we haven't done yet. But it's definitely only depends on the metric. So so I should maybe say the definition of the canonical metric in the general case, general situation now. So the motivation is as follows. We know that in the Riemann surface case, we have not just holomorphic one forms, but we can also have the anti-holomorphic one forms. And we know by probably we do not even need to use Hot theory, but like at least by Hot theory, all the harmonic one forms are either holomorphic or anti-holomorphic, linear combinations of holomorphic and anti-holomorphic one forms. So up to a constant, this thing is actually the same as C times the supremum of harmonic. So here it depends on how one define the. So the constant depends on your convention for defining the inner product in harmonic one forms. It's probably something like 1/2 or 2 or something like that. But we can define this. So the implication is that for Riemannian metric, for Riemannian manifold, we should let the canonical metric be defined as supremum of omega equals 1 omega harmonic one form so omega of V. So here the norm on harmonic one form is the usual Hodge norm. So the norm of a vector is just the vector, so yeah, the usual one. So the norm of this square equals the integral of omega, something like this. And yeah, it depends on convention of star. But if we consider complex value forms, then it depends on convention of star. Sometimes in the star they define the star as as the real star together with a conjugation, and sometimes not. But let's just, for simplicity, let's just make everything real. In that case, this is the definition. Yeah, so with this definition, the conclusion that we have is that we still have the convergence of the DCAN, and yeah, and since we do not have any restrictions on the covering, and even if we have the restrictions on the covering, the universal cover of a general k-dimensional manifold can be very complicated. It does not have to be a disk, so we can't really say much about whether or not the limits are the same. So this is the statements of our current, the current state of our theorem. So any question? Yeah. So if there are no question about the statement, I'll just briefly say about say something about the different steps of the proofs of our theorem, and we will mostly focus on this case. So one definitely follows from two, because of course a Riemann surface. For given a Riemann surface, we can just put any Riemannian metric on it, which is conformal to the Riemann surface itself. For example, you can just use the hyperbolic metric or any other metric. Then in that case, we know that because harmonic one forms can be written as the sum of holomorphic and holomorphic one forms, we have that equation that I just erased. So the canonical metric defined using the Riemann surface case is a constant multiple of the canonical metric, the generalized version of the canonical metric. So 2 will imply 1. So we will only care about the argument for 2. So let's see. So we just recently posted a paper which contains a partial proof of the second statement. So we will discuss that, and also we will say something about how to go from the partial result to the statement 2, which we will try to write down as soon as possible and post online. So an intermediate step for the proof of statement 2 is as follows. Let omega n be the measure of volume form defined using Dn. We will show that omega n converges, and from 1 we will show that Dn converges. So the overall strategy of the proof is that we just follow the proof in that appendix of that paper by Macmillan. I think it's about entropies with regard to covers. I don't quite remember the title, but if you Google entropy, then that's and then his name, then you get the paper. But so we mostly just follow the same outline as that proof, and just basically exchange each step to the kind of argument that's needed for the more general situation. So the outline is as follows. So firstly, how do we use the fact that so if we replace this with some other situation, so we will need to use the fact that pi 1 Sn equals h. So to do that, we consider we need to make use of this. So to do that, we consider a covering S tilde to S, where pi 1 of S tilde equals h. Of course, we only need to consider the case where h is of infinite index, because if h is of finite index, all the coverings will be finite and it will stabilize eventually. So there's nothing to prove. So this will be an infinite covering. And also pi 1 S over H is a group. Because we are always considering normal coverings. The intersection of normal coverings will still be a normal cover. So we call this group G. Then geometrically, what we know is that around every point, as n increases, because the fundamental group will converge to the fundamental group of the infinite covering, there will be a larger and larger neighborhood around each point, which will be isometric to a larger and larger neighborhood of the corresponding point in the infinite covering. Isometric to larger and larger neighborhoods of the corresponding point. In this, and there's a way to restate this thing, the measure or volume form defined using dn. So let's make a notation for it. We call it mu n. Then we can verify. This is just by simple computation. That mu n on a set A equals the supremum over all the omega. Let's consider the let me see. Mu, the canonical. So this one is the volume form from the canonical on S. So consider all the one forms, harmonic equals 1, omega harmonic on S, and then the supremum of the integral of this form just the integral of the form itself on the set A. So this is A. You can verify just by computation. This is true. Well, we are taking supremum over all the forms of norm 1, which are harmonic on a set. So this tells us that if S prime is smaller than S, an open submanifold, then we have I should use the other side. Then we have the canonical form using S1 for any set A, and then A is inside S prime. So we know that this set will have to be greater than or equal to mu A. The reason is as follows. This one means that we are taking maximum among all the harmonic one forms defined on S prime. Well, any harmonic one form defined on S prime can also be thought of as a harmonic one form. Can also be thought of as a one form on S by like zero extension. So, and on this side, we are taking maximum among all the one forms on defined on S, which is harmonic on the whole set S. Well, because S prime is a subset of S, if you have something that's harmonicity is a local property. If you have something that's harmonic on a larger set, then it is also harmonic on a subset. So let's just suppose we have some form which maximizes this value, which takes on the supremum for the mu A with superscript S. Then we can restrict our form to just S prime, and then consider another form where the everything on the outside will be 0, and only then we know that because we are making something non-zero into 0, the norm will be decreasing. Well, when we take the supremum, of course, we can replace equals 1 with smaller than or equals to 1. Then that element where everything outside S prime gets sent to 0 will be some element that satisfies this property with regard to S prime. So the corresponding, so it tells us that the supremum for this value with regard to S prime here will have to be greater than or equal to the supremum for this thing with regard to S. So any question? Yeah, that's the key argument. Oh, that's one of the key ingredients in the proof. So this is because harmonicity is local. Now we can combine this with the geometric observation. It will tell us that because if we have some like Sn, and then we have S prime, well, because Sn increases, there will be larger and larger neighborhoods around a point which will look roughly the same as a larger and larger neighborhood in S prime. So in other words, if we delete everything that's not in this large neighborhood, according to this, the canonical, the volume form will increase. So this tells us that the lim sup of mu n let me see, when we delete it, it will become larger, and which will be the same as the so if we call the volume form corresponding to the covering S tilde to S be mu tilde, then the result will be lim sup of mu n will be less than or equal to mu this. So we have inequality on one. So we have this inequality. If we can further show that the integral of mu n on the surface S is the same as the integral. So here, mu. In other words, the definition of mu tilde. I should write it down explicitly. Here, mu tilde is the volume form of d tilde, which whose pullback this is on S, whose pullback on S tilde is the canonical metric. So, in other words, both this side and this side are actually defined on the compact surface. So it's possible to say whether it's possible now to take limits on the left-hand side and say that the lim sup of the left-hand side is no larger than the right-hand side. Okay, so with this one, we just need one other statement in order to show that these two are exactly the same. The other statement that we need is that the integral of the surface of the manifold. I was using the term surface, but here S is a higher dimensional, arbitrary dimensional, like Riemannian manifold. So mu n equals well, this is due to a classical statement by this is due to a important result with regard to the theory of L2 homology. So this is Luke's approximation. So this is the second ingredient of our argument. With Luke's approximation, together with this inequality, we will be able to show that the volume forms converges. And actually, in the original argument by McMullen, instead of in the surface case, instead of using Luke's approximation, one can just use, for example, the Gauss-Bonnet theorem. But in general, we will need this as basically as a replacement of the Gauss-Bonnet theorem. And all this is in a paper that we recently posted on arXiv. And since we have carefully written down everything, I think there shouldn't be like a lot of any further so the probability of having some gaps in this argument is probably low. In the remaining part of this talk, we will talk about something that we have only had a draft but haven't written in all the details. So there's still some possibility for the remaining part of the talk to have some gaps, although I don't really feel like there will be any further gaps. So all these have been posted, and next we will. So this one basically prove this the intermediate steps of the statement 2, of something that I have erased, which is that the volume form will indeed converge. And so there's some just a few words about this convergence. So here the convergence is in the sense that the volume form integrating on every set will converge. In other words, it's a weak convergence. Depending on the terminology, I think it should be weak convergence. It can be strengthened into pointwise convergence of the volume form. So here the volume form can be thought of as a section on the K form, on the bundle of line bundle of D forms on the manifold, where D is the dimension of the manifold. So the way to strengthen this into pointwise convergence is because the reason that it can be strengthened is because in all these definitions and calculations, we are using harmonic forms. When harmonic forms has a nice property that it's the root of some elliptic equation. So we have the whole the whole machinery of elliptic operators, which can guarantee very nice regularity conditions. So we can basically assume all kinds of regularity, and following more or less the same strategy as in Macmillan's proof, we can strengthen this convergence from weak convergence to actual pointwise convergence. So next, we will try to move from the convergence of the volume form defined by the metric to the convergence of the metric itself. So the idea is as follows. If X is a vector field on S supported on a neighborhood of some point, we can define the magnitude of X under the canonical metric with regard to S as S defined as the supremum omega length 1 omega harmonic 1 form and X omega. We can define this thing. So recall the definition of the canonical metric. This one is more or less just the average of the lengths of the vectors on different points inside this support. So in other words, if the vectors are all like in the same direction, then this one will roughly just be the length of the vector. So this is the risk. However, the benefit of doing something like this is that we can define either way. Yeah, without the square it still works. Yeah, there's nothing wrong without the square. Yeah. So the reason that we consider a vector field instead of a single vector is that now we are doing integration, so it's probably easier to say. Oh, I see. So the supremum, okay, the integral of this of the some omega. So this is some any measure on S. So for example, we can choose omega as the measure defined by the original Riemannian metric. Then this is the average of the value of this vector, the length of these vectors under this.
Right now, omega is used in two different ways.
I see. this. Yeah, so we have some averaging. Now, exactly the same argument as before tells us that we also have monotonicity. If support of X is less than is included in S prime, which is in turn included in S. So this, so because of exactly the same thing here, we know that the lim sup of this. So for any given vector field with a small support, the lim sup of the magnitude of the vector field under the metric d sub n will be less than or equal to the value of the magnitude of the vector field under the metric d tilde. So we only need to show that these two are the same. Well, we know that we have a sequence of metrics, and we know that the volumes of the volume form defined using this sequence of metrics will converge to the volume form of another metric. If the metric does not converge, the only possibility is that in some direction it's stretching, in some other direction it's shrinking. So there must be some vector up to after choosing some suitable subsequence. There must be some vector whose limit as n go to infinity will have a magnitude, will have a length that's larger than the length of the same vector under the metric d tilde. And also there will be some vector whose length will be smaller than the same vector under the metric defined d tilde. So let's just pick this to be a vector. Consider some vector x so that dnx is limit after taking subsequence, we can just take the honest limit. This one is so lim sup is less than or equal to this. Okay, so lim sup. So if this one is larger than d tilde of x, then pick a parallel vector field supported near the point P. Then this one will be greater than so this one will be contradictory with the corresponding statement of this thing under the magnitude of the vector field. So this one implies lim sup will be less than or equal to. Yeah, this one will contradict with this statement. So the contradiction tells us that it's not possible for some of the vectors to stretch and some of the vectors to shrink. So the length of all the vectors will be literally just stay the same. And if you have like length of all the vectors being the same, then the Riemannian metric will have to be the same. So this is the argument. Any comments? And a last comment. So the setting of infinite sequence of normal covers can be generalized further into the Benjamin-Schramm convergence. So in other words, basically, we just want to we just want that in most of the so actually the fact that the normal cover is only useful in two situations. One situation is that it is a normal cover, so it has a deck transformation, so it's possible to pull back the limit. So it's possible to define some corresponding metric on the base, where the canonical metric on the cover is a pullback of such a metric. The other property is that, like locally, as n increases, it will look more and more. It will look more and more similar to the original shape. It will be isometric to a large disk on the universal. On the infinite cover, where the radius also grows. So as long as so there's a way to generalize the concept of normal covers so that both of these features are satisfied. So as long as you generalize the definition of a sequence of normal covers in such a way that both of these are satisfied, then the whole argument works without any modification. So that's a possible generalization. And lastly, there's an interesting question, which is that what exactly are the limiting metrics? So now this argument tells us that we will have a limiting metric, and by some harmonicity stuff, we can even say a lot about the regularity of the metric. So it will be smooth, and basically as smooth as you want. But the question is how to calculate them. So in some situations, in the surface case, if the surface is so in the surface case, because everything is conformal invariant, and if you have a surface of genus greater than, if you have a hyperbolic surface, then the universal cover will be the disk, and the conformal the conformal group of the disk will send every point to every point else, so to every other point. So there's essentially only one possible conformal invariant Riemannian metric on the disk, which is the hyperbolic metric. So in the surface case, we can just deal with the limit that way. But this is, on the other hand, this is something that's highly dependent on the fact that the unit disk has really a lot of symmetry. So for example, if we consider the group H, the intersection of all the pi1 SNs to not be identity group, but say the commutator subgroup of the surface fundamental group, then it will be an interesting question to understand what the limit would be. And also we can consider all many other kinds of subgroups of infinite index in the surface case. And for higher dimensional case, it's somewhat similar. So if you can somehow build, if all the surface we start, the free manifold we start with is a compact hyperbolic free manifold, and the metric is the hyperbolic metric itself, then this will tell us that when we go to the and then the sequence of covers will approximate the universal cover. Then the universal cover will be the three-dimensional hyperbolic space with the hyperbolic metric. And because of the large isometry group on the three-dimensional hyperbolic space, we can see that the canonical metric will indeed converge to the hyperbolic metric. But in general, for a free manifold, it will be interesting to see what kind of limit will this process give us. And a possibility is that, in a previous paper, in a paper that we posted last year, we dealt with the case of the limiting metric for the case of graphs. So in the case of graphs, there's some relation between the limiting metric with the Green's functions on the infinite graphs. So in other words, potentially there could also be a way, even though there may not be a way to writing down the limiting metric explicitly for any cases, there may be some way of representing the limiting metric using some using the solution of some interesting partial differential equations or integration equations. But that's something that we haven't done yet. So I think that's all I have prepared. So any questions or comments?
Okay, I missed your last comment.
Yeah.
For the generalization to the n-dimensional manifold,
Yeah.
if you further assume the intersection of pi 1 is identity,
Yeah.
then the limit of the metric becomes hyperbolic?
No. So it's like if in the free manifold, if the metric is if the metric we start with is already hyperbolic, then then the universal cover will be the hyperbolic hyperbolic free space. Well, because of the the large group of isometry in the hyperbolic free space, the canonical limiting metric will have to be proportional to the hyperbolic metric. But that's much weaker than the situation in the two-dimensional case, because in two-dimensional case we can see that the Hodge norm is conformal invariant and not metric invariant, not just metric invariant. Yeah, but like for general free manifold, I don't know how to do it. And my guess is that there could be potentially some integration formula.
Okay. So in the classical Kazhdan theorem,
Yeah.
I guess you should have stated that the S is hyperbolic type.
Oh, sure. Yeah, I see. Yeah, sure. Yeah.
So are you saying that free manifold is also same? I mean,
It's a hyperbolic Riemann. Yeah. In the classical Kazhdan theorem, it is absolutely correct that in the statement they assume that it's something of genus greater than 1. But actually, the same argument works for torus. If you do it for torus, it's a kind of trivial. So you can see obviously that the limiting metric will just be 0. The limiting, so in other words, the length of every vector will be 0. Yeah, because the torus cover is always a torus.
Is there any reason? If your manifold admits some homogeneous metric, is there any reason the canonical metric also has to be?
Yeah, I think it has to be. Yeah. So in other words, if in the cover the isometry group is large, the canonical metric of anything is invariant under the isometry group action. So if the isometry group acts transitively on the space, then on the space that you are looking at, then the canonical metric will be the same.
Are there any further questions or comments?
Yeah.
Okay, let's thank our speaker.
Okay.